As we look at dipole-dipole attractions or dipole-dipole forces, we are first trying to determine whether our bonds are polar or not, and then connect to how polar that is. Remember, all molecules will have dispersion, but we only have dipole-dipole when there is molecular polarity. Bond polarity might cancel out, so we want an overall dipole moment. CH4 is nonpolar. The bonds themselves are nonpolar, and the molecule is symmetrical. CO2 has polar bonds. The electrons are pulled each way towards the oxygen, but they are pulled equally in opposite directions, and the molecule as a whole is symmetrical. So they have no dipole moment, and therefore no dipole-dipole attractions. CH3Cl and CH3F are both polar. We've got our carbon in the middle, and even though there's 3 non-polar bonds to the hydrogen, the chlorine or fluorine attached to that does have a large enough electronegativity difference to make a polar bond. Therefore, the molecule as a whole is asymmetrical. The C to F dipole is a greater dipole than the C to Cl. For that, you would need to know exact electronegativity differences. Carbon is right around 2.5, whereas fluorine is 4, chlorine is 3. So that chlorine to carbon bond, although polar, is barely polar. The chlorine carbon to fluorine bond is one of the more polar things that can be considered polar without becoming ionic. So because the polarity or the dipole is much greater in CH3F, which would be fluoromethane, fluoromethane has much stronger dipole attractions than chloromethane. That means it's much more likely to condense into a liquid and have a higher boiling point. The methane, the CH4, the carbon dioxide, the CO2, we know are also gases because of those weaker attractions. But on B, it asks about the same molecules, but a very different question. Dispersion forces are based upon polarizability and number of electrons, not just valence electrons, but total electrons, because the electrons, even in the inner shell, are a part of the electron cloud for a molecule. So methane, CH4 has 10, CH3F has 18, CO2 has 22, whereas CH3Cl has 26. So the methane is definitely the weakest, followed by the fluoromethane. Chloromethane has the most electrons, which could mean that it is the strongest. But as we saw in the previous set of videos, pi bonding or double or triple bonding allows for extra polarizability. And we should know that CO2 has some double bonds in it. Without more information, it'd be hard to classify those exactly. Maybe we would know that the CH3Cl is a liquid. That would give us indication that it is stronger IMFs. Or maybe we would know something about the vapor pressure, boiling point, or melting point of CO2 compared to CH3Cl. That would allow us to know. When we are given data, the data is the tiebreaker or is the bottom line as to what is attracted the most. And that's something we will come back to in practice a lot. We might predict a certain bond to be, or IMF to be stronger than another, but it's only when it's supported by data that we can know that definitively.